All right, chemistry, this is your second video lecture for Chapter 5, Section 1, talking about periodicity, specifically the history of the periodic table. Last time we talked about Dmitri Mendeleev and his first periodic table organized in terms of increasing atomic mass. But there actually were some problems with Mendeleev's table. Now, these weren't huge problems. The predictions that Mendeleev's periodic table was able to generate were phenomenal. They were incredible. It was widely respected. It was widely adopted. But there were a few small issues. For example, why didn't some elements fit in terms of increasing atomic number? Last lecture, I mentioned tellurium and iodine. On our modern periodic table, those are actually the opposite. They're switched compared to the way Mendeleev had them, because they didn't fit in terms of increasing atomic mass. Or why didn't elements exhibit periodic behavior? Some of them didn't. So why is this happening? According to their atomic mass, where they should be on Mendeleev's periodic table, they weren't showing that perfect periodicity. So the question is why? A man came along, an Englishman, Moseley. He helped to clarify some of those problems. Now, Henry Moseley lived from 1887 to 1915. Some of you history buffs might remember what was going on in 1915. But he was an English physicist who determined the number of positive charges in the nucleus, protons, remember, by measuring the wavelength of the X-rays given off by certain metals in 1913. Now remember, up until this point, after Ernst Rutherford's series of experiments, scientists knew that there was a positively charged nucleus. And in fact, they also knew that there was some aspect of neutron in there, some neutrality. However, but the ability to count the individual protons, the number of positive charges in that nucleus, did not happen until 1913. Henry Moseley was able to do this using analysis of X-rays. Now, this man was killed by a sniper in Turkey during World War II, and many people think that England, Britain, lost a future Nobel Prize winner, and the reason this is because the Nobel Prize is not awarded to dead people. You have to be alive to receive a Nobel Prize. Now, if you think about the way we organize our modern periodic table in terms of increasing atomic number, the ability to know the atomic number is pretty darn significant. So you better believe that if this scientist was not killed in action in World War I, that he most certainly would have received a Nobel Prize. All right, taking a look at his contributions, mostly in the periodic table, protons and atomic number. This is where those things come from this man and his X-ray analysis. X-ray experiments revealed a way to determine the number of protons in the nucleus of an atom. Again, this was not possible before then. There was just this relatively large, or relatively small amount of positive charge that you could relatively measure. The periodic table was found, based on that, to be in atomic number order, not in atomic mass order. Because remember, Mendeleev was organizing his elements in terms of increasing atomic mass. And for the most part, that generates an accurate periodic table. But when we organize them in terms of increasing atomic number, everything falls into place. Everything falls into place. For example, this explained that tellurium iodine anomaly. Even though one of these elements, obviously, has a larger atomic number, it has a slightly smaller atomic mass. That's because the number of neutrons can vary between different elements. But this was able to explain that weird occurrence, that anomaly. And so with this perfect periodicity, with this ability to predict the properties of elements in place, we were able to develop, not we, he, Henry Moseley, was able to develop the periodic law. Remember, periodicity, things happening at regular intervals. So the periodic law states that the physical and chemical properties of the elements are periodic functions of their atomic numbers. Okay, because this was different from what Mendeleev thought. He thought that they were functions of their atomic weights or atomic masses. But again, Moseley was killed in battle in 1915, and he was only 28 years old. Now let's talk about some things that Mendeleev did not know existed during his time. If you're paying close attention to the way that his periodic table was set up, according to those increasing atomic masses, you will have noticed none of the noble gases were there. They were not represented because he was completely unaware that they existed. And that's kind of understandable because they're noble. They don't react. And that was a large way, a major basis upon which scientists were able to identify the existence of something is when it reacted. So if something doesn't react, you're not able to see it very readily. So let's take a look at these noble gases. So helium was discovered when it was seen as a component of the sun. Now, again, no one had traveled to the sun. Still, no one's traveled to the sun and taken a sample of the sun and studied it in a lab. They found out that helium was an element that was a component of the sun, a fairly major component of the sun, about 25%. It was based on the line emission spectrum of sunlight. Again, taking sunlight, diffracting it, looking at the individual wavelengths of light that compose it, it was seen that there was a particular element that showed a specific line spectrum, and that was helium. That was in 1868. Later on, a man named William Ramsay discovered argon, yet another noble gas. Same guy on a roll, he finds helium on Earth because the first time that helium had ever been observed, it was observed in the sun. So it actually took quite a long time, almost 30 years, to find it on Earth. Again, it's very difficult to observe these noble gases because they don't react. Keep that roll going. Ramsay discovers krypton and xenon, another two noble gases, just a few years later. And coming up at 1900, get someone else in on it. Frederick Dorn discovers radon. All right, so this is one of the groups of elements that Dmitri Mendeleev was completely unaware existed, the noble gases. A few others, and completely understandably so, the lanthanides and actinides. We talked about those when we went over the periodic table earlier. The early 1900s, the elements from curium and lutetium, that's number 58 and number 71, they were separated and identified, also known as rare earth metals, but less than 0.01% of them are naturally occurring. Okay, so you can see why it would be very difficult to discover those and describe them. The actinides, their discovery, and not necessarily discovery, it's more like a synthesis, the ability to make those elements because they are not naturally occurring, they're man-made. Looking at thorium, number 90, through lawrencium, number 103. Again, Mendeleev had no way of knowing that these two groups of elements existed, the lanthanides or the actinides, because they were far beyond the technological capacity of that time to observe. And so there are three groups of elements Mendeleev was completely unaware existed: the noble gases, the lanthanides, and the actinides. And we've talked about this before. Both of these groups are pulled out of the periodic table, the actinides and the lanthanides, for space reasons. That piece of paper would simply be too long, be too awkward. And so what we see is something like this. We have the S block, we have the D block, and we have the P block. And what we do is we actually separate the S block and the D block, and we insert the F block. Yeah, this is how this looks on the periodic tables that we use in class and scientists use today. And realize if we didn't pull out that F block, the lanthanides and actinides, this is what our periodic table would look like, and this would be a lot more difficult to read because we'd have to print this so small. All right, guys, that's going to finish up the lectures for this section. I will see you next period.